Yeah, so that.
It's a pleasure to introduce Netanel Blaier from MIT, who's going to be talking to us about A-infinity categories.
Yeah, so thank you, and thank the organizers. Okay, this is going to be the first talk in a series about abstract A-infinity categories. So let me fix my conventions right now. We're going to have some standing assumptions. Can everybody hear me on the back side to the rest of? OK. So K is going to be a coefficient field, which would be fixed. All categories are K linear, which means they're enriched over K vector spaces. And our grading convention is homological, which means this shifts down in particular. And we're going to add some assumptions later. I should probably say that throughout this talk, usually I'll try to think A and curly B would be A-infinity categories. Tilde F is going to be an A-infinity functor. And finally, I should say that I'll try to be strict about writing Fuc when I refer to the Fucai category, so you won't get confused with the infinity functor. OK, so what's the goal of this talk? The goal is basically to learn enough homological algebra to make sense of the things Nix is saying, which would be, we'll be talking about this, which would really be this. And OK, and just one moment of apology. So this talk is going to be very, very dry. There is no escaping it. I hope that the third talk would be a little more exciting. All the things that I'm going to say, all these A-infinity structures and A-infinity functors, they're going to have a lot of equations, and a lot of these equations are going to look ugly. The point is, all this stuff has better definitions, like very good, very clean definitions using either operads or non-commutative algebraic geometry. But in the end of the day, you just have to go down and do the computation. It's going to end up with the same messy formulas. So what I think I'm trying to say is, don't zone out when you see all these formulas. They're not as scary as they look. And I'll try also to make it more appealing. So let me start with our first definition, which is a pre-category A, which is just, it consists of a data of a set of objects, which is ob A, and it consists for any pair of objects in A, we're going to have a graded vector space, which would be known as the Hom space. So right now, I have no way of composing anything, right? So an A-infinity category, Nick told us, is pre-category plus a way to compose things. So for every d bigger than 1, we have a way of composing the inputs. So I have an operation that looks like this. I have an operation that looks like this. Sorry. X1, X2, X0, X1, X0, X2. And more generally, this was d equals 1. This was d equals 2. And now I have an operation that's mu d. course, I forgot this should be 1. So let me denote them graphically. So this is a unary operation. We know these are differentials. You write this the binary operation, and this will be denoted graphically as this tree. This is a d-ary operation. And they satisfy the following compatibility condition, which is for every operation like this, we have some UA d minus L plus 1 AD AK plus L plus 1 UAL AK plus L AK plus 1 AK A1, and where L is to D and K is to D minus L. And this would be the sum of the reduced degrees, where reduced degrees is just degree minus 1. So let me write graphically what it means. Well, this condition just tells you that if we denoted, right, we had a tree, we had another operation, and we just sum over all the possible ways of grafting one of the trees into the other with the appropriate sign, and the answer should be 0. And this is all it's saying. OK, and just to stress out the fact that like we have a shift in degrees, the degree of this thing would be the sum of the degrees of the AI plus 2 minus d. OK, so what are these equations tell us? Well, so, OK. So what are the A-infinity equations tell us? So let's look at the first equation. The first equation is just mu1 of A equals 0. So we know what that means. That means our unary operation is in fact a differential. Then we have mu1, mu2, AB equals plus minus mu2, BA plus minus mu2, B, mu1 of A. But this is just a Leibniz rule. And the third equation, which is probably the best reason why this is also called the infinity associativity equation, measures the failure of this operation to be associative. OK, so this operation, the third equation is basically tells us that mu2 is associative, but only up to mu1 of mu3. The failure to be associative is measured by mu3, basically. So mu2 CB A is plus minus mu1 mu3 C E A plus minus mu3 u1 C B A plus minus mu3 C u1 B A plus minus mu3 C B u1 of A. OK, so and the key point is just when you have operations on the chain level, you can't really expect them to be like to fall into an algebraic structure that's it's non-homotopy on the nose. I mean, in real life, things are never actually like associative. They're always associative up to a higher homotopy, but you can find order because this higher homotopy is associative up to higher homotopies, et cetera, et cetera, et cetera. So finally, let me introduce like something that makes this a little nicer, which is the bar complex. So that's the sum of A shifted by 1 tensor D, which is just K sum over D sum over all composable elements Hom of xd minus 1 xd tensor Hom of x0 x1 d. So the point is, when we have an infinity structure, we can define a differential acting on this. This would be, let's say if I have an infinity structure mu, I'll write it down as d of mu. And this would be given by basically taking this, plus this, plus this, plus, which is just the same as summing over all ways of sticking an operation here. And the purple one? Okay. Yeah. Okay. So let me just say we just go and we sum over all ways of sticking an operation here. So here we just put a mu L, and we sum over all possibilities, K's and L's. And so the infinity equations, so this, right, this is a degree 1 thing. And all I want to say is when you look at this from this perspective, then this being a differential is exactly the same as the infinity equations. So what we basically just defined, you can think about an infinity structure as just being a differential on the bar complex. So this is a very natural equation. Any questions so far? OK, good. So examples. Which we have. OK. So, well. Yeah. So example 1 is, of course, well, every DG category is automatically an infinity category, and you just need to set differential to be this, and the product to be this. And the higher operations to be 0. So every DG category is an instance of an infinity category. Another example, which might tell you why this infinity structures are very natural when it comes from like geometry. So you can think about having a closed manifold M with a Morse function f on it. And when you look at this, well, we know how to take, let's talk about the Morse-Smell-Witten complex, right? The Morse-Smell-Witten complex of manifold M and a function f is generated by the critical points of f, and I'm going to say it's graded by the Morse index. Do you need to say what it is? No? OK. So we know how to define a differential on it. It's made by counting, like, right? We count moduli spaces of trajectories of f. And we know how to define a product on it. We choose some kind of a perturbation, and we study, this is a point P, it's point Q, or maybe bounded by P0, P1. This is P1, this is P2, this is P0. So this is the mu1, this is the mu2. But what happens, I mean, the product in Morse theory is not associative on the chain level. It's associative on cohomology, but it's not associative on the chain level. So what happens when you want to study the associativity of this? So now you have two ways of composing free elements in Morse theory. You can study configurations of Morse graphs that look like this. Does everybody see what I'm doing? I'm composing a mu2 with a mu2 from here.
What does the new style? Just spend one sentence to explain what you're.
Okay. What I'm doing is I'm taking 3 critical points, which is, let's say, P1, P2, P3. And I want to think about writing down. Now I have 2 different ways.
Just explain product.
Product?
Yeah.
Okay. I have 2 critical points, and I want to look at the moduli space, which equals the intersection of 2 ascending manifolds and this descending manifold. Of course, this is not compact. I will need to compactify this, and I will compactify this using broken trajectories. And I will have some kind of a moduli space, and I can count the number of trajectories in that thing. And this is going to give me some kind of a product, right? I'm going to. Of course, this is, you can define this product without a perturbation datum. But we haven't, I'm glossing over the perturbation datum as we glossed over also in the case of the Fukaya category. This is, OK, so let's say that you have this, and you also have this. So these are 2 different ways of composing these critical points, right? So what you can start looking at is some kind of an interpolation between them, where this is a finite Morse trajectory. In the middle, you will have something like this, and then you will have something that looks like this. So these are finite Morse trajectories, and you have a parametrization, right? When the length goes to infinity, this trajectory breaks, and this corresponds to the composition of 2 mu2s. So you have an entire, now you have an entire line of possible operations. And this would give you a higher product. The moduli space of this would give you a mu3. And you can see that this is kind of an example. You can see exactly from the Morse relations, from the breaking of these trajectories, what does it mean if I take mu1 of mu3? You can count and you see that you explicitly get the infinity equations. So this is like a simpler example of why you would expect that these structures would appear in geometry. Any questions on this part? This is a finite length. This is a finite length Morse trajectory. Yeah.
What do you formulate besides the moduli problem?
Well, to formulate the moduli problem precisely, what you need is perturbations.
Just before saying that, I think maybe just the not curly line is an infinite length, or at least one direction infinite length.
Yes.
Morse trajectory.
Yes.
And then the curvy line is in both directions finite.
Yes. Does that help? Phrasing, I can't phrase it exactly, but that would be like kind of a different talk on yeah, so, OK. And finally, we have the example we've seen before. In the case of the Fukaya category, we had an operations, right? We've seen next talk we had objects, which were Lagrangians. And we had morphism spaces. We had Hom spaces in the Fukaya category. And we had morphisms that were exactly these operations. Go from the Hom of ls minus 1 ls tensor, tensor. And we were counting these maps that go from disks into our ambient manifold, right? And we had some decorations here, like what Lagrangians are we supposed to go to, etc. And this would be ls minus 1, and this would be ls. Okay. So these are 3 examples of like infinity categories. So we saw also the Donaldson-Fukaya category, right? And we said that this was like the cohomology level category. So it seems the room gone quiet. Was this example more confusing than helping? If this was an example, right? The purpose was not to confuse it. The purpose was to help. Don't lose. I mean, if that was confusing, please refocus on the algebra. Given an infinity category, we can define the homological category H of A. And this has the objects are the same object as A. And the morphism spaces are Homs with respect to the mu1. And the composition operations, well, u1 is 0, and composition operation, let me denote it in the usual way, which is A2 times A1, where these are cohomology classes. This is the following thing. And this is an ordinary k-linear graded category, except the possible lack of identity morphisms. So let's fix that. So if H of A has units, which means it's a category in the usual sense, we say that A is C-unital. And from now on, all our categories are going to be C-unital. And this is going to be, from now on, a standing assumption. At our list of assumptions, all infinity categories we deal with, first we'll talk, are C-unital. OK. And I should probably mention my small comment, but there is also, of course, a variant. There is a variant of this, which is called H0 of A, which is exactly what you think it is. It just retains the cohomology in degree 0, and everything else is the same. OK. So next. Yeah, usual classical. Yeah.
Unit usually for monoidal category.
No.
Unit morphism.
Yeah.
It's unit.
Yeah. No monoidal.
Unit morphism.
Yeah.
Principle is morphism on Lagrange itself, which is not defined.
Okay.
Yeah.
So you have to.
Unit morphism.
Yeah. Thank you. OK, on to part 2. That was the basic definitions. Let's now talk about like functors. So if we have A and B, which are 2 infinity categories, then a functor, an infinity functor, f between A and B is the following piece of data. It's going to be a map on objects. And it's going to be multilinear maps, which look like this. They go from Hom of xd minus 1 xd tensor Hom of x0 x1 into Hom over A fx0 fx1 going to be 1 minus d. And if I satisfy the following equation, which I'm going to write here, and I satisfy sum over all possible partitions of d URB FSR AD minus SR plus 1 FS1 AS A1, that equals sum minus 1 to the sign FD minus L plus 1 AD AK plus L plus 1. I want to continue this equation here because I think it's more legible. Okay, just say I'm continuing it upstairs. ULA AK plus L AK plus 1 AK A1. And okay. What is it? What? You mean this?
Yes.
I just meant that like I'm continuing this equation here.
I understand. It's long form. What is the meaning?
What's the meaning? Oh, yes. What's the meaning of this equation? Well, the meaning of this equation is as follows. Think about it in terms of the bar complex. Wait. Yes, okay. Well, if you have, let's say that you have A and you have B and you have some kind of an F, then you can form the bar complex. Let's say this is the bar complex interpretation. And you can form this, you can form this, and you can form a functor TF, which is just be made by taking a bunch of elements here and applying, summing over all the possible ways of applying functors to them, right? So you just apply the functor anywhere you can, and you get a functor between the two bar complexes in this way. What the equation says is exactly what you think it is. We have two chain complexes, right? What is the natural condition on the map between two chain complexes, right? Think about TF of DA should be DB of TF, which just means it's a chain map. And if you open this up, this is exactly this condition.
When you say all possible ways, you mean you apply F and compositions?
I mean,
And no.
I'm taking this tensor product, I'm breaking it up into as many groups as I can. Just stick.
What's the degree of this map? Because we start with degree N.
It's a 1 minus, this is a 1 minus d degree map.
Yes, I mean, okay. You start up from N tensor product. If you apply F, you get again N tensor product.
If you apply F, you get back N tensor products.
Yes, and you want to get one, meaning that you are allowed to apply this and
well,
or what?
I mean, no, because I take, each one of these things is multi to 1, right? So I take this, I break it up. Let's say that I take like a tensor of 3 elements, right? And I apply 1f to this and 1f to this of different degrees.
It mimics the bar complex.
Yeah, it
Bar
makes.
complex consists of direct sum of all possible.
Yeah,
Yes,
all
but
possible.
F was still from A to B.
Yeah, so
Yes,
so it will,
but it had multiple. There was FDs,
the map
right?
will start with if you came to this.
Maybe. I mean, the bar complex has it's a co-algebra grid, right? So basically,
Yes.
it's any morphism co-algebras, right? With respect to differential will give you a morphism F like this.
You're asking if any morphism of co-algebra, is
Commuting with the co-derivation
should give you something like this. Not sure if.
collection of that.
Yeah, I think that is correct.
Yes.
Yes.
That's correct.
Yeah. Okay. So is that clear? Yes. Okay.
Maybe you can give the geometric example of the modes, that might be like.
Yeah, I'm actually, since I don't think that I should repeat the example with the Morse trajectories. I have a feeling that like it wasn't well received.
Maybe you can just give it to Amit after.
Yes. Yes. Okay. There is an example, I should say, but it will take more. I mean, there is like a geometric thing that gives you an infinity functor and Fukaya categories. But that's like, I don't know a lot about it. There is like a quilts thing that's supposed to give you like infinity functors. I mean, you can make like a geometric definition. There is a geometric meaning also to infinity functors in this like Fukaya world.
Or you can just take an isotopy of Lagrangian submanifolds that will give you an infinity homomorphism. I mean, they're associated infinity algebras.
Okay.
But that's also.
That's also.
Now, for algebras, there exist two different kinds of maps. One is just a map, just an algebra. The other is Pareto equivalence, kind of bimodal.
Bimodal, yes.
Here, you definitely can also consider kind of
Correspondences, bimodal.
correspondences.
Yes, this is what, I mean, I guess the more geometric way in the way that they construct quilts, which I should not talk about because I don't know it and I haven't prepared it. If I understand correctly, they do it by something that's very close to a bimodule. They have a correspondence by m times n. Yeah, yeah, yeah. It's like a push-pull construction from a correspondence, yes. Okay. So, anyway, let's make the following observation. See how much time do I have. So we make the following observations, which is mu to be f1 of b, f1 of a, plus mu1 of b, f2 of ba, equals f1 u2 ba, f2 b u2 of a, plus minus f2 u1 ba. So what does this tell us? It tells us that f1, sorry, I mean the conclusion of this equation is just that f1 respects u2 up to homotopy by f2. So it almost respects composition. It's almost a functor. So we can define a functor in the homological category. So what we want to do now is say that if we have let's say that we have a functor f, an infinity functor that goes from a to b, we want to define h of f, which goes from h of a to h of b. And this functor is going to act on objects by sending x to fx, and it's going to act on the morphisms by taking a and sending it to the cohomological class of f1 of a. And this is an ordinary, but not necessarily unital functor. And we say that this functor is unital if the cohomology functor respects the unit.
Now, if you consider both A and B are DG categories,
Yes.
is the morphism between them as infinity category the same as DG categories?
Is an infinity morphism between DG categories the same between?
Just morphism.
No, there are more morphisms. That's exactly okay. Yes, that's exactly what I wanted to say. So I'm actually this is like an excellent point. So the point is like this. Okay, I should probably actually every infinity category is kind of a cheat. Every infinity category that's weakly unital is quasi-isomorphic to a DG category that's strictly unital. So we actually did not add any objects. So you might be wondering why did we decide to add an infinite amount of operations to define an object we could define with 2? And the point is like, Yeah, but the point, like, the morphisms are different. The morphisms solve all this problem. Think about it as the difference. Let's say that you were just interested, I don't know, in polynomials, for example, but you wanted to invert polynomials. I mean, you have the whole problem of roofs. Let's say that you want to invert, even if you just care about, polynomials, if you want to invert something, suddenly you will start having, like, power series, right? So the point is, like, the nice thing about adding all these higher operations is with a very simple condition, like an infinity quasi-isomorphism, you can always invert it. For example, everything like in this category, we'll see that when we pass to the derived category, we don't have to localize. This is why it's so excellent. Okay.
So which has more morphisms? The DG category?
The infinity category. Even between two DG things, there are more infinity like.
It's clear that any morphism between DG algebras is a morphism.
Yeah.
It's infinity.
Yeah.
They
Yes.
actually have embedded.
Yes.
But it's not subject.
Yes.
They're
It's
on there.
more morphisms, and you have sufficient morphisms to make like a lot of things like work, to correct a lot of problems that we had. Hmm? What? What? Show? Okay, so let me just define what I just said. I say that F is a quasi-iso if HF is an iso. I say that F is a quasi-equivalence if HF is an equivalence. I say it's homologically full and faithful if, like, H of F is full and faithful, etc. All these concepts mean exactly what you think it means. So let me give an example. You just mentioned of a quasi-equivalence. The problem is when we define a Fukaya category, like, we have all this extra junk, extra data that we need to use, perturbation datums, etc. And we would really like the Fukaya category to be independent of them. Unfortunately, it's not. But it is independent, let's say, up to a quasi-equivalence, which is what's really important for us. So this is like an example of like a natural quasi-equivalence in the context of like Fukaya categories. Change the perturbation datum. So okay, which time do I have? I started at 30, right? I have like 17 minutes. Okay, that's good. Okay, so let me make the following remark. Okay, composition of A-infinity functors which is just made by sticking F everywhere you see. That's strictly associative.
There is one important, one things about categorical, usually.
Okay.
The most important relation is that functors from one category to another is a category, not just a set. Is it true that functors from one infinity category to another infinity category is an infinity category?
Yes, I'm just gonna, yes.
Right.
This is like preempting. So this is strictly associative. Can't put enough, like. And okay, now I want. Oh wait, you were asking. I'm saying the composition of two infinity functor is strictly associative, right? So it's actually, I mean, if you want to like, it's actually like a DG category, I think, or something.
It's strange.
Wait, no, wait, no.
It is strange.
Two categories.
Yeah, okay, yes, but it is strictly associative. Yeah. So yes, this is strictly associative. I don't know if it like answers, but is it? Things two categories. Wait, the functors between the functors between.
Nothing to do with.
Yes, yes. Sorry, yes, yes,
Yeah.
yes. Let me just say yes. Of course. Oh, okay. So let's say that I am being given, right, two infinity categories, A and B, and let me define the category of functors between them. And category of functors between them, well, the objects are going to be obviously the functors, and the morphism are going to be morphisms between functors, which just means natural transformations, right? So we're going to have, it's actually called prenatural transformations. And they include the following. This is G's grading. So let me say what's the greedy. It's the following thing. They include a family T, D, where D is bigger than 0. And this is the infinity category you wanted, right? You wanted between two fixed categories. You have the category of functors. Objects of functors, and morphisms between them are natural transformations, which are families of these maps that we're going to describe, and then we have composition maps. Yes, that's what you wanted. Okay. So we don't just include T0, which is an assignment which sends every object A, right, into a map that goes from Hom G, B, f of x, g of x. But you also have maps like this, TD, which go from Hom A, xd minus 1, xd, tensor, Hom A, x0, x1, and this goes into Hom in the category B of fx0 and gxd, and this grading has g minus d. And this is called prenatural transformations, the morphism in this category of functors between A infinity categories. And there is a mu1 and higher composition on it. The formula is quite horrible. I'm not going to write it. And natural transformations are called the things with the mu1 kills. So they're the closed ones. A natural transformation is a prenatural transformation, which is the family of maps at the side. There is also composition maps, because this is an infinity category. I don't write them down because the formula would be really long. I'm saying that the definition of a natural transformation is some kind of a prenatural transformation such that mu1 is 0. So it's actually the closed prenatural transformations are called natural transformations. Yeah.
Now,
yes.
the second important thing in category theory is unity.
Yes.
So
there is a Yoneda embedding here. I'm not going to do it. I mean, modules are easy to define here as they are easy there. And there is a Yoneda embedding. And you can actually, OK, all the things that I'm going to say in a second, which is triangle, can all be done by doing this by universal properties, Yoneda embeddings, everything. But this is a talk of 1 hour. So I'm going to take a shortcut. This is like, and instead of going through like the Yoneda embedding, what I'm going to do is give you a construction. Go around it. Exactly. And it's also practically, I mean, when you actually do computations, Yoneda embedding is like great, but it embeds your category that you can control in something that's like insane. Yes? Okay. Yes. 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 Function. What? This is what? The objects are the functors, I said, and the morphism between them are natural transformations.
Yes.
What was the? I don't understand. What?
Right?
Yes.
You have a focus of transformations.
Yes.
That's not what you want to consider, right? You consider the homological aspect. I mean, H0 of the focus.
I think the question is why it's called the prenatural transformations in this terminology.
It's a terminology question?
You can have two categories, right? One of them is A infinity category of functors.
Yes.
Between A infinity categories. And the second one is just category, right?
Just usual category.
The usual category of just functors between.
Yes, just the
okay.
homology of the A infinity category.
Okay. You want to take let me just try and follow. You're saying what would happen if I take H0 of the I'm not.
What is the category you want to consider?
I
You
can't
take
hear.
H0 on the complex combination of transformations.
Yes.
You take the whole complex.
When you take the
Is
whole.
the category which you are now going to consider of functors to the infinity categories, infinity categories, or is it just the usual category? And if it is just the usual category, then how do you find it?
I'm not.
Probably already said it.
Yeah, I'm not really sure at the moment, like exactly what you're asking. So maybe we can talk about this later. I don't think that. Do you want it? Do you hear it?
Yeah.
So there is an A infinity category of functors between
right.
two things. And so you can take H0 of that,
Right.
which is an ordinary category.
Yeah, sure.
Both these things are, well, for some purposes, all you care about is
Yeah, sure.
looking on the.
Just which
I mean,
one does he want to consider now? So does he just take
I don't think you. I don't think he needs. I don't think he needs
I
not
didn't
to
understand.
continue to consider it. It's just
Yeah.
to know that there are these
Yeah, sure.
No.
two
For
notions.
complexes, it's different. Isn't it?
Yes.
For complexes, it's different. Instead of H0, you consider just Q.
Sorry, can we?
It's not the same.
I'm just.
Let's
Yeah. Can
move.
let's just like. Yeah. I mean. So. Let me just like continue. We'll talk about this later. Okay.
Now just, sorry, I repeat my question.
Yes.
So if you consider in terms of bar complex,
Yes.
so bar complex is some compound with differential.
Yes.
You have another bar complex, another. Could you give explicit construction of a new bar complex? I'm not asking to do it. Which would be represent functor category? It's a kind of explicit simple construction in terms of bar complexes.
I mean, you always have the harm. I mean, but not the harm.
All right.
I'm not sure. Yeah, I'm not
Yeah,
sure.
continue,
It's a
continue.
natural. Yeah. Okay. Natural question. I'm not sure. So wait. Let's say we want to define the derived category. Okay, so we have complexes. And I know that we haven't talked about derived categories yet, so just this is going to be in a later talk, right? But let me just say, okay, we have to undergo, when we go into the bin category, we have to undergo through a certain process. We take a complex, we take homotopy, we localize, etc. So in the infinity world, we have similar. We go from A infinity to twisted complexes. And this is the process we go to get D of A. And if we want to get the code be completed, when we have another construction. And the nice thing about this is all these constructions are very, very explicit. And all these constructions are finite, and there is no localization necessary. So, okay, let me start by saying what's an exact triangle in infinity category. So I define the following infinity category, which has its objects Z0, Z1, Z2, and has its morphisms dimension 1 vector spaces, which are Z0, Z1, Z2. And for here, this is just the vector space of a unit, space of a unit, vector space of a unit. This is k times x1, k times x2, where this denotes a degree. Yes. You have Z0, Z1, Z2 in this following triangular diagram. Between where are arrows from each to itself, which are k times EZ0, EZ1, EZ2, right? And there is an arrow between z0 and z1, which is generated by x1, x2, x3, where this is degree 0, degree 1, degree 0, degree 0, and degree 1. Right? This is supposed to resemble, you know, an exact triangle. Okay. So, and what are the compositions in this category? Well, the compositions look like this. We have -1 to the a u2 ezk.
No condition at all?
Hmm?
No condition at all on this x0, x1, and this?
I'm writing the compositions.
This is the condition.
Yes. Okay. Okay, these are all the composition. These are all the higher composition maps.
So suppose our category is just DGH.
Yes.
So what do we do with these? Objects are just.
Wait, but what I defined a specific category, right?
Yes.
What do you mean, like, suppose
So
it's
Specific category.
yes. This is T3.
Just as the element.
Yes.
Okay.
Yeah. Now the definition. Let me give the definition. This is like the category where the ideal, like, exact triangle lives. Yeah. And an exact triangle (0a) is a diagram that looks like this. You have y0, you have y1, you have y2, you have c1, you have c2, you have c3, where this has degree 1, and we want to have an A-infinity functor f that goes from this category, T3, into A, such that h of f of zk is yk, and h of f of xk is the morphism ck. Okay. So every
Now I
triangle.
repeat my question. So suppose A is the G category.
Yes.
So why is it? So what is it in this case?
Is the same as the usual one.
Exactly.
Yeah.
Here's my question.
Yeah. Okay.
Why? Starting with new 3 would be. So what's?
It's 1/3 of
What do you mean?
Is it true that in this case, such morphism as we say is usual triangle?
Is it true that in this case, you mean the triangulate? Is it like in the yes, that's exactly what I'm going to say. Okay, let me. Can I just say it? Okay. So the point is this. And let me know if it answers your question. If we have an A-infinity functor, then the cohomology level functor always sends exact triangles to exact triangles, and we'll say that an infinity category is triangulated if it is, say, closed under shifts, and every morphism AC1 in H star of A can be completed to an exact triangle. And theorem is if A is triangulated, H0 of A satisfies TR1 to TR4, which means it's triangulated in the sense we're going to talk about next. Did that answer your question?
Okay.
Except that what can explain what is closed and the shifts.
Yeah, I'm not going to. I mean, it's basically, okay.
The same as the cone of something to 0?
Yeah, but I don't want to define cones right now. I just want to define twisted complexes and define cones in the twisted complex. I mean, if to define, well, to define a cone, you probably need to start doing your Neda embedding, and you define it as a module, and then you save it an object quasi-represents that. And then, okay, I want to take the quick, short path, which is two twisted complexes. Twisted complexes, you always have an object representing it, and then just say it like that. Yeah. Yeah, as I said, everything that basically we defined has definitions by Neda embeddings, infinity modules in the classical sense. We're taking like kind of a shortcut. So we just say twisted complexes. So this is a construction that undergoes in two stages. One is the additive enlargement, and this is called sigma A, and where we allow formal direct sums as objects. And that means we take sum of something finite, xi, ki formally, where xi are objects in A, and ki are numbers in Z. And then we take morphism spaces. The morphism spaces are going to be a hom between two of these formal sums. Well, in the hom between these two formal sums, it's going to look like this. Yj Lj minus Ki. And we're going to write it as a matrix for the following reason. This is just notation, right? But this notation is convenient because, well, let me take this entire board to write this down. Yeah, there's a convenient stopping point right after like the next 5 minutes, basically. Yeah, that's what I'm saying. We also started late. So multiplication is uk in sigma A consists of taking AK A1 and just writing down what you would imagine if these were all matrices. So that means you sum over all I1, IK minus 1, mu AK, AK, IK minus 1, J, I1, I1. So just think about doing the multiplication as matrices. So far, that makes sense, right? Everybody happy with that? Sad with it? Okay. Okay, so And the next phase. Yes.
If your category already has sum, is a sum.
Yes.
Can you get an isomorphic object to the sum in the formal category, or I mean?
I can tell you that in the twisted complex case, if you already were triangulated, then you're going to get something that's quasi-isomorphic. The additive enlargement, I don't know, but I presume yes, although, yeah. Okay, so now the twisted complex, which stopping point. So stage 2 of this construction. So now we have complexes. So the next stage is going to look at the twisted complex category, which is TWA. It has the following objects. It has x and delta x, where x is the sum xi ki. It's the object on the additive enlargement. And dx is going to be the following differential. It's going to be a map degree 1 such that dx is strictly lower triangular, and the sum of uk dx is 0, where here k goes from 1 to infinity. And this is finite because this is strictly triangular. The morphism are going to be exactly the same thing as if we just ignore the differential. So if I take a where the sum here, yeah, this is objects in sigma a, which is the additive enhancement. So it's a finite.
Oh, so it's finite.
Yeah, and here we just ignore the differential. So this is really just Homs, the same Homs that I defined before. But, and this is going to be the important part, but the multiplication is deformed. And the multiplication is going to look like this. The multiplication operations in a twisted complex setting, let's say that I take AK A1, then now I'm going to sum over all this. And I'm going to take UK plus 0 plus IK sigma A. And now I'm allowed to insert this delta k's. This delta k is 1, this A1, x0, delta x0, I0 times, IK times, IK minus 1 times, and probably say that the point is this category turns out to be triangulated, and you always embed into it, and then you can just go and define cones in it. The last functor that I used was that, okay, maybe I should save it for the first 5 minutes of the next time. Any questions?
So, could you give some kind of maybe not formally correct way to think about the second operation? First is quite clear. We want to add all the
Yeah.
sums. What is this second?
The second operation, I'm not sure. Yeah.
Other questions?
Yeah.
Not side, not.